Welcome to the CompTIA A+ Prepcast presented by baremetalcyber.com. Motherboard interfaces form the foundation of how internal and external components communicate and receive power within a computer system. These interfaces include data pathways, expansion connections, power delivery points, and front panel control headers. Each plays a specific role in the overall operation and performance of the system. A clear understanding of where these connectors are located and how they function is essential for anyone assembling or troubleshooting hardware. The A+ exam includes questions across multiple domains that require familiarity with these interfaces, especially during hardware installation, configuration, and fault diagnosis. The SATA interface, which stands for Serial ATA, is one of the most common motherboard connectors used for attaching storage and optical devices. SATA cables provide a dedicated data path from the motherboard to devices such as hard disk drives, solid-state drives, and optical drives like DVD or Blu-ray readers. The interface includes a separate data connector and power connector, typically provided by the power supply unit. SATA supports hot swapping in systems that allow it, meaning drives can be inserted or removed while the system is powered on, provided the operating system and motherboard firmware support that feature. M.2, commonly referred to as M.2, is a compact interface that connects directly to the motherboard and is used for high-speed storage devices and communication adapters. It is a slot-based interface that can support either SATA or NVMe storage protocols, depending on how the slot is wired on the motherboard. Not all M.2 slots are identical, and using the wrong type of drive in a mismatched slot may result in the device not being recognized. In addition to storage, M.2 slots are often used for wireless communication modules that enable Wi-Fi and Bluetooth, making them a versatile feature on modern motherboards. PCI Express, or PCIe, is the high-speed expansion interface used for connecting various peripheral devices to the motherboard. It uses a serial communication protocol that offers high bandwidth and low latency, making it ideal for devices such as graphics cards, network interface cards, solid-state drives, and capture cards. PCIe slots come in different lane sizes, including X1, X4, X8, and X16, where the number indicates how many data lanes the slot supports. Devices must be installed in compatible slots to ensure adequate performance, and the slot's physical size must match the card's connector. Comparing PCIe slot sizes reveals important performance and compatibility details. A slot with fewer lanes, such as X1, offers lower bandwidth than a slot with more lanes, like X16. However, many devices are backward and forward compatible in terms of slot size, meaning a smaller card can often fit into a larger slot and function correctly, although with reduced bandwidth. Conversely, a high bandwidth card placed into a smaller slot may operate at limited functionality or not work at all. For optimal performance, the slot size and lane configuration should always be matched to the specific requirements of the installed card. Legacy expansion interfaces, while increasingly rare, may still appear on older systems or specialized hardware. The PCI interface, or Peripheral Component Interconnect, was the standard before PCIe and uses a parallel signaling method. Though slower and less flexible, PCI was widely used for sound cards, modems, and early network adapters. Another now obsolete interface is AGP, or Accelerated Graphics Port, which was designed specifically for graphics cards before PCIe became the standard. While neither interface is relevant to modern systems, awareness of their appearance and limitations may be useful for working with legacy hardware during troubleshooting or migration. USB headers on the motherboard provide internal connection points for the case's front panel USB ports. These headers come in different versions, including USB 2.0, USB 3.0, and USB Type-C. Each header supports one or more ports, and typically has a keyed connector that prevents incorrect orientation during installation. Proper alignment is essential, as incorrect connections can lead to non-functional ports or, in worst cases, short circuits. These headers are often located along the bottom edge of the motherboard and may be labeled clearly to assist with installation. The front panel header is a critical interface that connects the case's physical buttons and indicators to the motherboard. These headers include pins for the power button, reset button, power LED, hard drive activity LED, and internal speaker. The pin layout is often color-coded or printed directly on the board to indicate the correct placement for each cable. If these connectors are improperly attached, the system may fail to power on, or the status lights and buttons may not function correctly. Proper connection of the front panel header is essential for user interface and power control. Random access memory, or RAM, is installed into dedicated slots on the motherboard, usually labeled as DIMM slots. These slots support DDR memory modules, such as DDR3, DDR4, or DDR5, depending on the motherboard's design. The number of memory channels supported affects overall system performance, and proper slot population is required to enable dual or quad channel operation. Latches on either side of the DIMM slots secure the memory sticks in place and must be clicked into the locked position to ensure reliable electrical contact. Improperly seated modules can cause boot failures or system instability. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. The CPU power connectors play a critical role in delivering stable and sufficient power directly to the processor. Located near the top edge of the motherboard, these connectors are typically 4-pin or 8-pin configurations, known as EPS connectors. They supply the dedicated voltage required by the CPU, independent from the main motherboard power. In high-performance or overclocked systems, using the full 8-pin connector ensures better voltage delivery under heavy load. Failing to connect this properly can result in system instability or prevent the system from powering on altogether. The 24-pin ATX power connector is the primary source of power for the motherboard. This connector, supplied by the power supply unit, delivers electricity to all integrated components, including memory modules, chipset features, and onboard controllers. It is usually positioned on the right edge of the board near the memory slots. A locking latch ensures that the connector is securely attached and prevents accidental disconnection. Without this connection, the system will not receive the necessary power to initialize or operate any of its functions. Fan headers are motherboard interfaces that allow the system to control cooling devices such as CPU and chassis fans. These headers are labeled according to their function, with typical labels including CPU_fan for the processor cooler and SYS_fan for system fans. Fan headers may have 3 pins or 4 pins. 3-pin headers support voltage-based speed control, while 4-pin headers enable pulse width modulation, also called PWM, for more precise fan speed regulation. Fan speed profiles can be adjusted through BIOS settings or third-party software to manage system temperature and noise levels effectively. Audio headers are internal connectors used to link the motherboard to the case's front panel, headphone, and microphone jacks. Typically labeled HD_audio, these headers must be connected correctly for front panel audio devices to function. Improper connection or failure to plug in the audio header will result in non-functional front ports, even if the rear ports are working properly. The header is usually located in the bottom left area of the motherboard and is keyed to prevent misalignment. For users relying on headphones or microphones connected to the front of the case, this connection is essential. The CMOS battery serves a small but vital function in maintaining system configuration between shutdowns. This battery powers the real-time clock and retains BIOS settings even when the system is unplugged. The most common battery type is the CR2032, which is a coin-shaped lithium cell mounted in a horizontal or vertical socket on the motherboard. If the battery fails, the system clock may reset to default values, and custom BIOS settings such as boot order or voltage configurations will be lost. Replacing the CMOS battery restores the ability to retain these settings, ensuring consistent operation across power cycles. Higher-end motherboards may include diagnostic tools like debug LEDs and postcode displays. These features are particularly useful during system assembly or when troubleshooting hardware failures. Postcodes correspond to specific initialization steps in the system boot sequence, allowing users to identify whether the CPU, RAM, GPU, or boot devices are causing an issue. Debug LEDs may illuminate or flash to indicate component-specific problems, such as memory errors or CPU faults. These tools reduce guesswork during troubleshooting and are valuable additions for users building custom systems or performing frequent upgrades. Onboard video connectors enable the use of integrated graphics provided the installed CPU includes support for such features. Common onboard video outputs include HDMI, DisplayPort, VGA, and D versus I. These ports are located on the rear I/O panel and are functional only if the processor has integrated graphics capability. If a dedicated graphics card is installed, these onboard ports are typically disabled. For users who do not require a discrete GPU, using onboard video can reduce system cost, power consumption, and complexity while still offering basic video output capabilities. BIOS flashback and USB update ports are specialized interfaces found on select motherboards. These features allow users to update the system firmware without requiring a CPU, memory, or storage device to be installed. This is especially helpful when using a newer processor that is not recognized by the board's original BIOS version. Flashback ports are often color-coded and labeled clearly on the rear I/O panel. Users insert a properly named firmware file on a USB drive, connect it to the designated port, and initiate the update using a dedicated button. This feature ensures broader CPU support and simplifies recovery from firmware issues. Wireless interfaces are sometimes built directly into the motherboard, offering integrated Wi-Fi and Bluetooth connectivity. These modules typically connect through M.2 slots or internal USB headers and are paired with antennas that attach to the rear I/O panel. The antennas may screw into coaxial connectors or clip onto internal mounting points, depending on the design. Signal strength and performance are influenced by antenna placement, with external antennas offering better range and reliability. Including wireless features on the motherboard reduces the need for additional expansion cards or USB dongles. In summary, understanding motherboard interfaces is essential for anyone assembling, upgrading, or troubleshooting a computer system. Key connections include SATA for storage, PCI Express for expansion cards, and M.2 for high-speed devices. Power delivery relies on both the 24-pin ATX and 8-pin EPS connectors, while fan headers and audio headers support cooling and front panel connectivity. Diagnostic tools, video ports, and wireless interfaces add further functionality. Familiarity with these connections and their locations ensures successful system integration and is a critical skill for passing the A+ certification exam. Thank you for listening. Please visit baremetalcyber.com for more cybersecurity information, podcasts, books, and more.